This lecture explains the changes in a low-mass star after it leaves the main sequence. On the main sequence, the star's size is very stable as the inward gravity is balanced by outward pressure. Main sequence stars are divided into two classes. The low-mass stars, less than about 8 solar masses, quietly leave and eventually become white dwarf stars. The high-mass stars go out with a bang. They become neutron stars, pulsars, and black holes, as we'll discuss in the next learning module. A star of 1 solar mass stays on the main sequence for about 10 billion years. When there is only non-burning helium ash remaining in the core collapses. The resulting higher pressures and temperatures lead to hydrogen fusing in the shell outside the core. When the core shrinks, its gravitational pull gets stronger. Stronger gravity leads to higher pressure, which leads to faster nuclear reactions in the hydrogen-burning shell, which leads to more energy produced. The plasma in the core is completely ionized due to the high temperatures. The electrons are pushed together very tightly. A property of electrons, due to their quantum behavior, limits the degree to which they can be squashed together. Electrons are fermions, a type of particle that is limited to only 2 entities, one spin up and one spin down, sharing a quantum state. When it is packed as tightly as it can be, it is called electron-degenerate matter. It is so dense that a piece the volume of a standard 6-sided die would have more than 1,000 kilograms of mass. Degenerate matter behaves very differently and contributes to the process of stellar evolution. Although fusion stops in the core, which is now filled with the electron-degenerate matter, outside the core, hydrogen burns. Astronomers call this the hydrogen shell burning. As more helium ash piles atop the core, the interesting and counterintuitive behavior of electron-degenerate matter is revealed. The core gets smaller. The more massive electron-degenerate matter is, the smaller it is, which is the opposite for most matter of everyday experience. Electron-degenerate core behavior triggers a chain of events that dominates the 1 solar mass star's evolution for the next 50 million years. Degenerate matter produces stronger gravitational forces. The increase in pressure and energy production results in larger size and lower surface temperature. The star becomes larger, more luminous, cooler, and redder. It travels to the land of red giants on the HR diagram. This red giant has a radius of more than 50 solar radii and a luminosity several hundred times the solar luminosity. However, the core is much smaller and denser. With the extensive solar surface area, the star cools at a faster rate, so that the temperature of the star is dropping even though the luminosity increases and the interior is hotter. That's what makes it redder. Figure 12.5 illustrates the journey of a 1 solar mass star off the main sequence and along the red giant branch. As the star exhausts the hydrogen in its core, it leaves the main sequence and moves upward and to the right on the HR diagram, cooling the temperature of its vast surface but increasing its luminosity. Since the surface layers regulate the cooling so that it can't become cooler than a red giant type, the rate of increase in luminosity increases as the star progresses. The textbook offers this visual analogy of a snowball rolling down a hill. The larger it gets, the faster it grows. Similarly, the cycle of hydrogen shell burning surrounding a degenerate helium core feeds on itself. As the helium core shrinks, its density and temperature increase. When hot and dense enough with the core temperature of 100 million Kelvin, helium fusion begins. Helium fuses to carbon via the triple alpha process. Figure 12.6 diagrams the triple alpha process. The red giant phase ends when temperatures in the central core rise high enough to new nuclear reactions to begin. At this stage, the small, dense core of electron-degenerate material reaches the critical temperature for helium fusion. Within seconds of helium ignition, the thermal pressure to the point that the helium core literally explodes. This explosion is called the helium flash. Helium fusion results in a rapid collapse of the star and subsequent heating of the surface. The fusion reaction in the core allows the core to expand. The pressure in the outer layers subsides, allowing them to contract. Once helium fusion begins, the star travels on the next leg of its journey along the horizontal branch. The name horizontal branch refers to the diagrams of older stars clusters, where there is a sequence of stars sticking out from the red giant along a horizontal line, where they have nearly constant luminosity. Helium fuses to carbon in the core, while hydrogen fuses to helium in the surrounding shell. The star progressively becomes smaller and hotter than a red giant. When the helium is used up in the core, hydrogen and helium fusion continues in the concentric surrounding shells. But the carbon in the core does not fuse, and the plasma in the core is non-degenerate. The star increases in luminosity and cools. These stars are called asymptotic giant branch stars, and for short, AGB stars. As the luminosity temperature radius relation prescribes, the radius also increases, and this time to a much bigger size than a red giant. The AGB star exceeds the size in luminosity of a red giant. As the star expands, some of its material leaves a stellar wind. This mass loss means the star cannot hold on to the outer layers easily. Eventually, the outer layers are ejected into space. The ejected material creates a planetary nebula. Note that planetary nebula have absolutely nothing to do with planets. The remaining stars shrink and become hotter. The remaining star shrinks and becomes hotter, moving rapidly from right to left across the HR diagram. The star ionizes the gas in the expanding outer layers, causing the planetary nebula that we observe. Planetary nebulae do not last forever. Eventually, the gas disperses. The first observed planetary nebula had circular appearances, hence the name, but now we observe examples with much more complex structures. The ultraviolet radiation from the white dwarf may ionize the gas in the ejected layers, causing them to glow. Here are more examples of planetary nebulas. The arrows point to the white dwarfs that will remain after the dust is blown away. The leftover core of the star remains as a white dwarf, with a mass of 0.6 to 1.4 solar masses, and about the size of the Earth. It is hot, but not very luminous due to small size. White dwarfs cool off because no nuclear fusion is occurring. Putting these pieces together, we have the stages of stellar evolution from the time the Sun-like star leaves the main sequence. After the hydrogen in the core is fully depleted, the star leaves the main sequence, first becoming a subgiant, then a red giant. The star does not expand and cool indefinitely. There are internal limiting processes. Buildup in the core of electron-degenerate matter leads to a helium flash that only lasts a brief moment. At that point, it becomes an AGB star, moving horizontally back toward the main sequence, infusing both hydrogen and helium. When the helium in the core is depleted, it has a carbon core. This non-degenerate plasma does not support fusion. Instabilities in the helium fusion lead to pulsing that ejects much plasma into space as a stellar wind. The remaining core is hot. It shrinks and cools. The luminosity declines with this cooling stage, and no fusion takes place. Eventually, the stellar wind blows the planetary nebula away, leaving just a small, hot, but not very luminous white dwarf. When fusion stops, the star becomes a dwarf. Sirius B is a white dwarf companion of the larger and brighter Sirius A. The white dwarf is considered dead, and it will cool gradually over a long time. However, there is a way to bring them back to life. The zombie natures of some white dwarfs will be discussed in the next lecture. Pearson Education offers this table showing the amounts of time the star spends in each step, and how big, luminous, massive, and hot it is. This graphic shows the entire evolution of a sun-like star, giving a relative sense of how long each stage takes. In summary, a low-mass star makes predictable circuitous journey on their HR diagram as it dies. It becomes a red giant, then an AGB star, then a planetary nebula, and finally a white dwarf.